Welcome back. In this video, we're going to talk about thinking as manipulation. In the previous video, we defined thinking as a process, as a mental process of manipulating representations. And we also said that there are two different forms of representation. Images, which is a pictorial form of representing information, and words or concepts, which is a non-pictorial form of representing information. Now, in this video, we're going to talk about the process of manipulation, how our mind processes, manipulates these representations that we've discussed in the previous video. So just to reiterate, thinking is defined as mental representation and manipulation. So it's manipulation, and there is no manipulation without the representation. So we need to talk about both. We did talk about representation in the last video. Now we're going to talk about manipulation. So here the question is, what is thinking as manipulation? Now, one way to think about it is the way we actually form concepts or representations. The representations can be images or concepts. And the way we form representation is through our experience, right? And for us to actually form representations, the memory system should be matured enough to form representations. So forming representation itself can be considered as a process of thinking. Forming concepts, as well as we discussed in the last video, is also a way of thinking, in the sense that we form concepts with repeated exposure to the objects. For example, dog. Initially, we have this. Kids develop this concept of any hairy thing looking would be a baba or a dog. Then later on, they learn. So through positive exposure, through positive and negative instances of experience with these objects, you form concepts. So these are basic thinking processes, but we're more interested in more complex mental processes of this sort. Basically, problem solving, decision making, and creativity. Now, if you think about it, these are all kind of similar in the sense that first let's look at each one of those individually. Problem solving. Problem solving is a process of finding a solution to a problem, and which we typically do by employing a strategy. And we'll talk more about this in a second. So problem solving is basically solving a problem, finding a solution to a problem. Decision making is also similar to problem solving, in the sense that you still find a solution to the problem, but you have several options to choose from. So it is selecting one from available solutions that would be a decision making. So it's a kind of problem solving where the solution you are coming up with is actually given to you, and you're selecting it from several other options provided to you. And the last one is creativity. Again, you can also think of this as problem solving, where you're trying to solve a problem with a solution, but you're not interested in any solution. You're really interested in finding a new solution, a novel solution. Now let's look at the creativity. So we said that creativity is basically finding a novel solution to a problem, not any solution. And there's this concept of divergent thinking versus convergent thinking. Convergent thinking is about thinking in a systematic fashion, or thinking leading to one conclusion. Divergent thinking, on the other hand, is not thinking about a solution, but thinking about various possible solutions. So you're just not interested in finding a solution. Instead, you're interested in as many solutions as you can. Creativity comes from divergent thinking. Now, best practices underlying creativity would be use of analogy. You can think of a problem and think of when you're trying to find a solution, you're thinking about other analogies that are similar or maybe not so similar. Maybe they're superficially similar, and in a deeper sense, they are not. So, using an analogy would be one good method. The other thing is you can come up with new ideas by combining already existing concepts. It's called conceptual combination, or you can build on a single concept, and it's called conceptual expansion. Again, we're not going over in detail about these different ways of thinking. What we're more interested in is actually talking about problem solving in general. Now, in this particular video, when we are talking about thinking as manipulation, if you can see, it's mostly problem solving, right? Decision making is also problem solving, creativity is problem solving. So we'll talk about problem solving in general in this particular video. So, some basics of problem solving before we move on to the specifics. For instance, in the following slides, we'll talk about different strategies people use to solve problems. For now, I just want you to give some basic idea of what problem solving is, some terminology that you will utilize in this concept, in this construct, in this context. I'm sorry. Now, in this problem, you see, you must move rings from peg A to peg C. You can move only the top ring on a peg, and you cannot place a larger ring over a smaller one. So this is these are the instructions given to you. Now, take a moment, pause this video, and think about how you would actually solve this problem. Again, this is the initial stage. The end stage is that all these three things would be here. Number three, ring number two, ring number one. And what you can do is you can only move only the top ring and onto a different peg, and you cannot place a larger ring above a smaller ring. So give it a try. Well, now the idea here is not to actually solve the problem. I'm pretty sure you'll figure it out. The idea is to talk about some constructs related to problem solving in general, and this applies to any problem solving situation, but we're going to discuss that in the context of this particular problem. When you have a problem in psychologists or cognitive scientists, they think about these terms: problem space, operators, and constraints. First, we'll talk about problem space. Problem space is this mental representation you have of the problem, which includes your understanding of what these things mean. It may also include some visual representation that you might be using to solve the problem. So everything there is in this particular space in your mind that you are working on would be a problem space. Well, what would be included in the problem space then? Well, in the problem space, there are operators and constraints. Operators are things that you're allowed to do. In other words, it says that you must move the rings from peg A to peg C. Well, you can move, although this is instruction, but you can move only the top ring on a peg. So you can move this to the next peg. That would be an operator. Operator are the allowable processes or allowable things in a given problem. Constraints, on the other hand, are the things that you're not allowed to do. In other words, it says that you cannot place a large ring above a small one. You cannot place a large ring above a small one. That would be a constraint. So we commonly use this terminology to talk about problem space, operators, and constraints. So problem space in this is this representation of the problem itself, which includes operators of your ability to move things, and the constraint is the fact that you cannot move or place you cannot move all the rings at the same time, and you can only move one, and you cannot place a big one over a small ring. Okay. Now, and understanding this terminology would help us understand the processes involved in problem solving. Well, I'm pretty sure you must have answered the question correctly, but we'll come back to that problem later. But let's talk about, now that you have some basics of problem solving. You know the definition of it. You also know the concepts, the constructs like problem space, operators, and constraints. Now let's look at the definition of problem solving again. Problem solving is finding a solution to a problem by employing a strategy. Well, then the next question would be, what are these strategies? There are several strategies one can apply, but the psychologists are most interested in these specific strategies: the trial and error strategy, insight, algorithm, and heuristics. And we'll talk about each one of these strategies. And because these are strategies, I named them as S1, S2, S4. So strategy 1, strategy 2, 3, and 4. Once we're done talking about the strategies, we'll talk about the roadblocks, the barriers to problem solving. In other words, barriers to adopting the strategies. And we'll go from there. So first we'll talk about strategies in general, starting with the trial and error strategy. Let's talk about strategy 1, trial and error. Remember this cage? Remember the Thorndike's law of effects? Well, the cat is placed in this box, and there is food outside, and cat has to figure out a way to get to the food. Now, guess what the cat does? Well, it tries several things, right? It hits the door, it does something and something till it accidentally hits upon this particular lever, right? And of course, it repeats the behavior. This strategy is trial and error. Try different things till you don't do a mistake. In other words, till the thing that you're working on, one of those things actually works. Then you continue to keep repeating those, the thing that worked. So trial and error is trying different things until you get to the solution. Okay, let's talk about the second strategy now, the insight. Now, for this, I would like to take this example. Now you see an upright triangle here with these dots. Your task is you have to move only three dots, only three, any three of these dots. By moving such, but by doing so, you have to convert this upward facing triangle to a downward facing triangle. So I want you to pause here for a second and see if you can find a solution to this problem. Well, I hope you try. Now, what did you do? Did you try every possible solution there is? Then that is a trial and error approach. You're trying different things till you find an answer. And most of the times, it may not work. Or the other thing people usually do is sit back and keep thinking about it till accidentally, or you come up with a flash of idea that leads to the correct solution. And usually in problems like these, when you actually keep thinking about stuff, the answers come to you eventually. So the actual solution for this problem is this. You're moving only three dots. The first dot you move is this. You bring it here. Oh, sorry. You bring it here, right? And you move the other dots. One here, the other here, as shown in this particular picture over here. So now, if you thought about it for a while, you'll immediately certainly come up with an answer that is called insight. Now, insight is a very interesting thing in the sense that you are coming with an answer from nowhere. But keep in mind that insight requires one to think about a particular problem for a prolonged period of time, over days, months, or who knows, years. Then you come up with an answer to the solution. One good example of this is Archimedes, and he was working on a specific problem related to, I don't remember the specifics, but the weight of the body immersed in water and the weight of the water that overflows. So he was taking a bath one day in a bathtub, and suddenly he realized the solution to the problem. Well, it did not just come to him, but he thought about it so much so that he was able to restructure his problem space. That's why we said that we need to use these terms, understand these terms. So he had a representation of the problem. Now, guess what happened in the story is that Archimedes would he was so excited that he would actually run in the streets naked, shouting "Eureka, Eureka!" Anyways, the idea here is that you can get insight into a problem to find a solution, but how? What happens? What exactly happens for insight to occur? Well, restructuring. The problem space gets restructured. You could see some connections that you did not see before. That is insight. Insight is finding a solution, and the only reason, or one possible reason, is that the problem space itself is restructured, or you have seen some actions that you can do that you haven't thought you would do. Another example I would like to give here, and I won't give you a solution to that, but we'll come back to that at the end of this presentation. Now think of 6 pencils. 1, 2, 3, 4, 5, 6. Now these 6 pencils are of same length, okay? Or you can think of 6 sticks or whatever you want, 6 particular lines of same size. What you need to do is create four different triangles. Not any triangles. These triangles need to be equilateral triangles. Equilateral triangles have same length throughout. So you need to create 4 different equilateral triangles using 6 lines or pens of same length. Well, keep thinking about it. Maybe by the end of this particular lecture, you'll come up with an answer. If you do, then that is because of insight. Then we'll talk more about insight then. Again, the problem is try to create 4 equilateral triangles with the length of the triangle equal to the length of the pencil by using 6 pencils. Okay, let's move on to the next strategy now. The next strategy number 3 is algorithm. Now, algorithms are step-by-step instructions or procedures for solving a particular problem. For example, if I ask you, what is 33 times 96? 33 times 96. Well, you may not answer right away unless you have some strategies that you've learned in your arithmetic class, but there is a way to find this. If given time, you'll definitely find a solution to the problem because there is a procedure, a step-by-step procedure to follow. And if you follow that, you have a solution. So algorithm is one such strategy that guarantees a solution to you. But it takes a long time. For example, problems like 2, 9, 6, 7, 8 times 3, 2, 4, 6, 7. Well, you can apply algorithm to find the answer, which is the actual process of multiplication, but it takes time. Same with insight. You don't just get an insight. By the way, did you find a solution to the problem about 6 pencils, 4 equilateral triangles? Keep thinking. So insight, again, you have to keep thinking till you get to the solution. So algorithms guarantee a solution. Algorithms guarantee a solution. So long as you follow the rules, you can get to the solution. Now, the programs, so the computer programs are algorithms. So when you enter a specific instruction, it has a software in it, a program in it that actually has step-by-step instructions to about what to do. Hence, you have the solution to the problem. Another example of algorithms would be think about the what is that? Watson. Have you seen Watson? Watson, the computer, the mega computer that actually won and defeated several Jeopardy winners, and it became a big thing in recent years. Well, even before Watson, um, this is Gary Kasparov, and who played with a computer. The question was, do you think computer would defeat a person at that time? Around that time when he played with the computer, people thought it's impossible. Computers cannot think like humans. They cannot, definitely, they can never defeat a human. But guess what? I think on the second or the third game, uh, um, actually, this computer, Deep Blue, I guess what it was called, it actually defeated Gary Kasparov. The way it defeated is not because it is thinking conscious like we are, but the fact that there are strategies that are built into the computer. These strategies are algorithms. Like if this, and this, then do this. If this, and this, then do this. So a set of instructions are created, and the computer lays its instructions based on the situations that are given to the computer, which is based on the way Gary Kasparov reacts or responds in that game. Now, keep in mind that as humans, no matter if we are Gary Kasparov or anyone, we are limited in terms of the number of steps you can go through, whereas computers are not. So again, the basic idea here is the algorithm, which is a set of instructions given for a specific problem to find a specific solution. Let's move on to the next strategy. Oh, by the way, did you find the answer to the question? How to form four equilateral triangles where the length of the triangle is equal to the length of the pencil when you're given six pencils of same length. Keep thinking. Well, algorithms definitely guarantee you a solution because of the set instructions. And if you follow the procedure, you get to the solution. Although they guarantee, the problem with the algorithm is that the real life problems do not have an algorithm. There is no algorithm that would guarantee you that you can become a millionaire. There is no algorithm that can guarantee you that you can become, or you, this is how you can become a doctor or engineer or a president of the United States or anything. So real life problems do not have algorithms. Well, there is closest we can get to the algorithm though. It's called a working algorithm. A working algorithm is one that doesn't guarantee you the solution, but at least it increases your chances of finding the solution. For instance, if you want to be a millionaire, well, you can practice, and go to the other smaller events and practice, test your memory, learn more, learn some mnemonic techniques, or try different things, and definitely it will increase your chances, but it won't guarantee you. It's a working algorithm. Let's say you want to become a doctor. Study studiously in college, in high school, then take pre-med, then go for MCAT, then MLE. If you do all these things, then the chances of you becoming a doctor are higher, but does it guarantee? No. So the problem with algorithm is that not all problems, in fact, most problems are ill-structured problems. They are not well-structured problems. Well-structured problems have algorithms, but real life has a lot of ill-structured problems with no specific algorithm to it. Let's talk about the last strategy, the heuristics. Now, heuristic algorithm guarantees your solution, A heuristic, it doesn't guarantee a solution, but it it gives you a um, quick rule of thumb, a quick strategy to quickly find a solution, which may or may not be the accurate one. So a heuristic is a guiding principle, a rule of thumb used in solving, but they don't guarantee you success, but definitely they'll save some time. Now, let's look at this example to kind of see which strategy is better, whether heuristic or algorithm in this context. Now, you must move two matches in here to form four equal squares. You can move any two matches to form four equal squares. You can pause here and keep trying. Okay, I hope you tried. I'm pretty sure you found the answer. Now, what did you do? Well, if you thought about each and every possible move you can make and do it methodically, then you're probably using algorithm. Well, definitely you'll come to a point where you find a solution to it, but it's going to take a long time. A heuristic is fine using a shortcut and say, okay, let me see. Maybe this is a stick. By just removing it would decrease this 5 number to 4 squares, right? So maybe I'll take this. Okay, I put it here. Then I take this one and put it here. So solution would look something like this. So 4. Again, it's like trial and error, but it's more than trial and error. It's like quickly trying to find a solution by looking superficially about the information. That's heuristic. So heuristics are these guiding principles, these rules of thumb, and the different kinds of heuristics. Again, heuristics are those strategies, those principles, those rules of thumb uh, that increase your chance of finding an answer, but that doesn't guarantee you, and it actually reduces the time you spend on the problem. And the three different heuristics that are well studied, and we can talk about each one of these: means end heuristic, backward working heuristic, and creating subgoal heuristic. Remember, we're talking about the last strategy, heuristics, and we're talking about three different kinds of heuristics. Now, the means end heuristic is when, let's say, this is your initial state and this is your goal state. Now, at each point, you measure the distance between the initial stage and the goal state and try to take one step at a time to reduce this distance between the initial stage and the goal state. So you make a move here, it reduces the distance, then you measure the distance and you take another move, and so on and so forth. That's the means and heuristic. Again, not all heuristics are helpful in all problem situations, but some are more useful in one than the other context. Um, Now, you might have heard this heuristic, backward working heuristic, where you're not starting from the initial stage, but you're actually start from the goal state. It's opposite to the means and heuristic. You're starting from the goal state and going through all the intermediary states till you get to the initial state. Then you, by doing so, you figured out how to go from the initial to the final stage. This is like a reverse engineering. Now, creating sub-goals heuristic. Now, mostly high school and college students use this. Remember, just imagine you have a final paper to write. You just don't keep writing without any structure. You kind of divide that into sub-goals, right? Okay, I'm going to write the introduction, then the method section, and then maybe the results section, then the discussion section. So you kind of divide your paper into sub-goals. And when you finish these sub-goals, then you have finished the actual goal. So it actually helps. It's one of the heuristics to help actually solve complex problems. We divide the problem into manageable chunks, and you attack each individual sub goal till you get to all the sub goals. And each sub goal may have further sub goals. So that is creating sub goals heuristic. And in the next slide, we're going to talk about one example of creating sub goal heuristic in one of the problems. Now, remember this Tower of Hanoi problem? This creating sub-goal heuristic is a very apt strategy here to actually solve this problem. Now, here, remember, you need to move all the rings from peg A to peg C. How would you do that? I'm pretty sure you know how to do it. You figure it out. One way to do that is to kind of create sub-goals, right? Well, first, sub-goal is to move this this ring here. The second one would be move this one, and third one would be to move this one. So for sub-goal one, you would move the third ring eventually and do everything you need to do to move to this third peg to this third ring to this particular peg. So what do you do for that? Well, one way you can do is put the smaller peg here, right? Put the second one here, right? And bring the first one over the second one. Then take this third one to the last peg. Something like this. Oops. Something like this. See that? So one sub goal is met. The second sub goal is to move the second peg here. Right? Well, easy now, right? You can move the first peg back to the A and take the second one and put it here. So sub goal 2 would look something like this. Well, sub goal 3 is pretty easy now. Now you have to move the third one here. So creating sub goal heuristic is actually dividing the bigger goal into smaller manageable things and working on the individual goals individually till you find the entire solution. So far we looked at problem solving, and we said problem solving is manipulating representations or symbols by using different strategies. And we talked about these 4 strategies. And within the last strategy of heuristics, we looked at 3 commonly studied heuristics. Now, the last thing we need to do is talk about the roadblocks to or barriers to solving problems or barriers to using strategies to solve problems. So the 3 commonly studied barriers or roadblocks to using problem-solving strategies. One is mindset, the other one is functional fixedness, and the other one is irrelevant information effect. Mindset is when you use the same old strategies that worked before, but it doesn't apply to a new problem. So we'll talk about it by looking at an example. Functional fixedness is difficulty in thinking about new ways of using objects in a given problem space. Again, we'll talk about that. Irrelevant information, in fact, is basically getting overwhelmed by irrelevant information, unable to capture the actual important operators or constraints in a given problem. So let's move on to the mindset and functional fixedness. These are the 2 things that we'll talk about. This is self-explanatory. So in this example, suppose you have a 21 cup jar, then sorry, 21 cup jar, 127 cup jar, and a 3 cup jar. Now, drawing and discarding as much of water as you like from this one, you need to measure out exactly 100 cups of water. How can you do this? There is 127 cups of water in this, and you have 21 sized and 3 cup sized jars. Think about it. Pause the video and try to find the answer. I'm pretty sure you can find the answer. Did you? Okay, well, the way to solve this problem requires you to reduce the relationship in algebraic formula. So what you can do here is think about, okay, you're going to take 21 out. So 127 minus 21 would be 106. Now you're going to take 3 cups jar twice. So it's basically B, which is this one, minus two, 1 cup of A and one jug of A and 1 jug of B. So it's like 127 minus 21 minus 2 times this. Now, the interesting thing about this problem is that in 1940s, a Gestalt psychologist by name Abraham Luncheon, what he did is that he showed participants with several of problems of this sort, and he gave problems that would solve that the participants could solve by using this same formula over and over again. Then he presented with a very simple problem where it just requires to use just 1 cup to draw the water out. What he found was that given that the participants saw the utility of using a particular formula over and over again, they would employ the same formula even for simpler problems. This tendency to rely on strategies that worked in similar situations in the past, but may not be the best solution to the present problem. That is mindset. Mindset is using the old strategy that worked before in the new situation, even though the situation is requires a simple solution or a simple strategy. That is mindset. Well, let's come to the functional fixedness barrier. Just imagine this situation where there are 2 strings hanging from the ceiling right here, but are too far apart to allow this person to hold one and walk to the other. On the table are there's a book of matches, then there's a candle, and a few pieces of cotton. Now, how could the strings be tied together? Take a moment, pause this video, and see if you can find the answer to the solution. Okay, I hope you tried, and typically what happens is it's difficult to imagine how you can use the things the usual things people say, like, "Hey, I can stand on this table and try to hold." Oh, well, you can. Is there any other way you can try to hold these 2 strings together? Well, one solution to this is actually using the candle to tie it, then swing it, then hold the candle. So you're holding the rope. So the solution depends on tying the candle to string. So failure to solve this problem is a classic example of functional fixedness, which is your inability to think about using a candle in a way that wasn't used before. Candle is typically used for other purposes, and the utility of a candle in this is novel, and unable to think that is functional fixedness. The last barrier we're going to talk about are the cognitive biases. These biases are especially applicable or act as roadblocks in a specific kind of problem solving situation called decision making. Remember, decision making is the process of solving a solution by choosing an option over the other when multiple options are given to you. So, so cognitive biases are more applicable in decision-making situations. So we're going to talk about three important cognitive biases, which act as barriers or roadblocks to correctly solving a problem or making the right decision. So one is confirmation bias, the other one is representativeness heuristics, and the third one is availability heuristics. So let's talk about each one of these. The confirmation bias is not changing your belief in spite of actually finding strong evidence against it. And you can see on social media the strong effect of that. Again, um, well, we move on to the next cognitive bias. The representativeness heuristic is when you think that the sample that you experience, it represents the population. Now try to answer this question. What is more likely? Which of these two instances is more likely if you tossed a coin 1, 2, 3, 4, 6 times? Is it this or this? Well, people typically say this is more likely because this is a combination of these things is more probable, or more we experience and we think that is a representative of the actual possibilities. If you look at the actual probability, they are equally likely. So that is representativeness heuristic. The sample you've experienced, you think represent the entire possible representation of the population. Now, coming to the availability heuristic as a cognitive bias, is well, let's answer this question first. Which is more frequent? Words beginning with the letter K or words with K in the middle? Well, people typically say it's words with K in the middle. Sorry, words with the K starting with the beginning with the K. The reason is that you can easily think of words with K. It's hard to think of words with K in the middle. Well, this decision then is availability heuristic. In other words, your decision is based on what is readily available to you, and this leads to errors in judging relative risks. Let's talk about the another cognitive bias of the gambler's fallacy. Now, just imagine if there is a machine, a slot machine, and has not made a payout in some time. What people believe is that playing on it will yield better results, more money now, given that it hasn't paid out money recently. However, the odds of winning any single bet is no different if you have lost 20 times in a row or have just started betting. It doesn't really matter. So this is gambler's fallacy, which is the mistaken belief that the odds of a chance event increase if the event hasn't occurred recently. Talk about the last cognitive bias, the overestimating the improbable. Now answer this question: which has a higher mortality rate, asthma, or tornadoes? Well, the answer is given to you. People typically say it is tornadoes, but actually it's asthma. So, due to media coverage and other factors, people tend to overestimate the likelihood of rare events, such as airplane crashes. They may base decisions on misestimating the probability of events, like driving across country rather than flying based on erroneous belief that it is safer. This is overestimating the probability. Overestimating the probability, improbable, sorry, is related to the availability heuristic. Most people think that the dramatic, vivid acts are more likely to occur than the commonplace ones.